Hello everyone, how are you doing? Let's see if it's working. Uh, yes, I think it does. I'll check in a few moments as well. Alright, so for today, the plan was today, don't worry, it's not a 3 hours live stream as last time. Yes, it does work. Yeah, by the way, last stream that I did for Complete Structure 1 IBHL, it went really well. I think the feedback was great, so I will be doing Structure 2. But today it's going to be like a small relaxed stream. So what we're going to do today is we will finish our test practice for IBHL paper 2 from Save My Exams. We started it a few days ago and well, last week I think. So I have linked part 1 and part 2 below, like in the comments of this video, and today we'll just continue. So we solved up till question 7, so today I will just continue from question 7. If you haven't watched the beginning of this, you can check the description, and also I have a link to this paper also in the description, so you can solve it on your own and then watch the video or just solve along with me. All right, let's start. So first, well, question 7. We have an equilibrium, and what is, write the equilibrium constant expression Kc. So we remember what Kc is. Kc, it's equilibrium constant. It is written as equilibrium concentration of the products to the power of their coefficients over equilibrium concentration of the reactants. And that's what I will do. So Kc for this reaction, it's products over reactants. So that's the product, CONH2 twice times, yeah, the plus changes into times concentration of gaseous water divided by concentration of reactants, which is NH3 to the power of 2 times CO2 to the power of 1. The power of 1 you don't have to write down. Remember, square brackets are essential. If you write it in round brackets, you lose a mark, even though in IB you don't really do Kp, but square brackets are reserved for Kp if you do A-level chemistry. You know what I'm talking about, but still for Kc, remember to use square brackets. Next question. Delta H for the forward reaction is negative. Yeah, delta H enthalpy change. Predict the effect on the equilibrium constant Kc when the temperature is increased. Well, let's see. Yes, one thing to remember, if you change anything else, if you change pressure, concentration, or whatever, Kc would not be affected. So Kc is only affected by temperature. And the logic that I will apply now to see how Kc changes, you can only apply to temperature, to nothing else, okay? That's the very common mistake. So if you shift equilibrium in some other way, not with the temperature, you cannot do what I'm about to do now, okay? Very important. So, all right, so we said that forward reaction is exothermic. We know that Kc is affected by temperature, as I said, right? Now think about it this way. So where would equilibrium shift if you increase the temperature? Well, you know that according to Le Chatelier principle, equilibrium would shift to the endothermic side. So if the forward reaction is exothermic by default, automatically the backward is endothermic. So you increase the temperature, equilibrium shifts left, right? So left. Equilibrium shifts left. And let's see what happens to Kc. So Kc, it's products over reactants. Yeah. So if you shift equilibrium to the left, what does it mean? It means that you decrease the amount of products. So the numerator decreases and you increase the amount of reactant. So the denominator increases. What happens to this fraction? Well, it gets smaller. Yeah. So Kc would decrease because equilibrium shifts to the left. And that's your explanation if you need to explain. Here we don't need to explain because they just say predict the effect of Kc. Well, it decreases. If you were to explain, you would say it decreases because equilibrium shifts to the left because the forward reaction is exothermic or backward is endothermic. Either way is fine. But remember, please remember, do it only for temperature, not for anything else. Next one. Predict what will happen to the equilibrium position if there is a decrease in pressure. Okay, decrease in pressure. What happens? So pressure affects only gaseous particles, right? So if the pressure is decreased, the system would try to oppose the change. So the system would try to increase the pressure, which means that equilibrium would shift to the side with more moles of gas. Okay, so decrease in pressure shifts equilibrium to the side with more moles of gas. On the left side, we have 2 plus 1. Remember to check that it's gases, right? So on the left side, we have 3 moles. On the right side, we have 2 moles, 1 plus 1. So it would shift to the left. Shift to the left. Right, let me check if I'm still live. Yeah, I think I am. And by the way, the chat is in subscribers mode. So if you want to ask questions, you can just subscribe and it will let you, just for safety reasons. Okay, so you can subscribe and it would let you ask a question. Next, the Kc value for the reaction is determined to be 2 times 10 to the negative 9. That's a very tiny one, right? So it means that forward reaction doesn't go well. Determine the magnitude of Kc if the reaction is reversed. This is a very common question in recent years in IB chemistry. So let's see in general, yeah. So how does Kc of forward reaction and reverse reaction, how can you connect them? So, well, let's just in general maybe let's do it for this reaction actually. Yeah, let's do it for this reaction. So we know that, I'll rewrite it. So the reaction is 2NH3 plus CO2 reversibly goes to CONH2 plus H2O. So that's my forward reaction. Yeah, did I do it right? Yeah. And we know that Kc for this reaction, we just wrote it down. It's CONH2 twice H2O divided by NH3 squared CO2. So that's the forward reaction, and that's the Kc for the forward reaction. Now they ask us about the reverse reaction. Let's write it down. Yeah, if your math is good, you'll spot the answer right away. But if it's like mine, let's rewrite it. So H2O, I write down the reverse reaction. Will the Kc change? Yes, it will, right? So because I flipped the reactants and the product. So what's the Kc for this reaction? Let's say this is Kc1, this is Kc2. Well, Kc2 would be NH3 squared. I still do products over reactants. Times CO2, that's a 3 by the way, yeah? Divided by CO NH2 twice times H2O. And now compare these two fractions. You see that Kc2 is just a flipped Kc1. Yeah, so if you know the value for that, well, let's write it down. So I know that I wrote them down, and then I understand that Kc2 is just 1 over Kc1. So because if you flip this fraction, you would end up with Kc2. Well, and now if you know the value for Kc1, we'll just plug it in. So then Kc2 would be 1 over 2 times 10 to the negative 9. And it's a very common question. So sometimes they would give you either a reverse reaction or maybe something else. Yes, so for example, maybe they would double the coefficients. Just write down 2 Kc's and then see how the fractions are related. Can you explain from the very beginning, please? Yes, I can see your question. Today we're just finishing the paper, but the beginning of the paper I linked both videos below. Yes, so we have the beginning in 2 other live streams, so you can watch those. 10 to the negative 9, and that is 5 times 10. Oh, that's so many zeros. 1, 2, 3, 4, 5, 6, 7, 8. So that's 5 times 10 to the power of 8. 5 times 10 to the power of 8. Yes. Next question, question 8. So salicylic acid has the structure shown below in figure 1. Draw the structure of the conjugate base of salicylic acid showing all the atoms and all the bonds. Okay, so all the atoms and all the bonds. Essentially they ask for displayed formula, right? What is a conjugate base? So conjugate base forms when acid loses a proton. Which part of this molecule would lose a proton? By the way, if you know the answer, you can write it in the chat. So we know that the acidic group, it's the COOH, yeah? OH would not lose a proton. These protons you cannot lose as well, yeah? At least not an acid-base reaction. COOH group is the one that would lose a proton, so your conjugate base would form when that proton is gone. If you lose any other proton, that's unfortunately a mistake. Yeah? So you just have to know that COOH is acidic group, so that's the one that's losing. And we have to show all the bonds. You know what, I'll write it here. So I'll just rewrite everything, and I'll just even keep the double bonds. Although, you know what, that's not the best way to draw the benzene ring. Yeah, we usually write it with the circle to show delocalization, but I'll just keep what's in the question. Well, yeah, that's your conjugate base. The proton is lost, and when H plus is lost, you get oxygen with, oh no, I like that, yeah, I covered it. Yeah, so you get the O with the minus. Fine. Next question. Predict what would be seen if a small amount of copper oxide was added to aqueous solution of salicylic acid when warmed, and write the balanced equation. Okay, well, let's write the balanced equation. Well, obviously would have a precipitate formed, right? Because salts of copper would be precipitated. And then this is just a reaction of acid with metal oxide. Well, let's write it down. So copper 2 oxide, the formula is CuO. And the salicylic acid, they told me to write it in this form, so I will write it HO, C6H4COOH, and CuO. Again, the reactive group, it's the COOH group, and you would just form a salt. The acidic residue, if I lose this proton, the acidic residue would have a charge of -1. Yeah, so HOC6H4. COO would have a charge of -1. Copper would have a charge of 2 plus. We know that because they told me that it's copper to oxide. It's a transition metal, so strictly speaking, it could be +1 or +2. They told me it's +2. And then you work with this formula in the exact same way as you would with any, ionic salt. So 2 goes, you crisscross the charges, right? So 2 goes to acidic residue, 1 goes to copper. So your formula would be that HOC6H4COO twice, yeah, to compensate the charge, and water, because salt, you get salt and water from acid and basic oxide. And then we just have to balance it. So if you put A2 here, okay, so about balancing, you don't really have to balance in such a way that you check every single atom. You could do that, but you see that, for example, this part, you can balance it as one thing. Yeah, so you need 2 of these because you put a 2 here. That's why I have to put a 2 in front of the acid. And then what changes is that, okay, now you have 2 hydrogens to balance. Well, there they are. And oxygen is there. You can double check. You can check all the atoms if you want. Yeah, that they're balanced. And you'll see if that worked. Well, it should have worked. Next one. Suggest with a reason whether salicylic acid is likely to be soluble in water. Yes, okay, well, let's see. So about solubility. We need to think about intermolecular forces. So normally a substance would be soluble in water if it has, well, if it can form hydrogen bonds, right? So the solute and the solvent, if they form approximately, like if they form identical intermolecular forces, if we're talking about simple molecular substances, then usually they would be soluble in each other. Of course, for example, if you know the rules for alcohols, yeah, so small alcohols would be soluble in water because they can form hydrogen bonds with water. Larger alcohols, not as much, because yes, they can form hydrogen bonds with water through the OH group, but also they have quite strong London forces from the hydrocarbon chain, yeah, which it's like overpowers the ability to form hydrogen bonds. And here, well, let's just, because the molecule is quite small, right? So I would assume that if it can form hydrogen bonds, then it would be soluble. Well, and it does form hydrogen bonds, and from 2 positions, right? So it forms hydrogen bonds from the COH group and from the OH group. So I would expect it to be very soluble. Yeah. Yes, so just with a reason. We say soluble because it can form hydrogen bonds. Yep, it can form hydrogen bonds through the COOH group and OH. By the way, hydrogen bonds with water. Yeah, I lost the mark here. If you don't say with water, that's not a mark. I'm very good at losing marks on such questions, so This year in A-level exam, I lost 2 or 3 marks in paper 1, so, and that was on definition and on emitting, something like that. Next, determine the relative molecular mass of salicylic acid using table 6. That's just MR, so, well, okay, so the formula was HOC6H4 COOH. Okay, so let's calculate it from the periodic table. Hydrogen, well, I'll just show it just in case. So hydrogen relative atomic mass is 1.01, carbon is 12.01, oxygen 16. Yeah. Okay, so I have hydrogen times how many hydrogens do we have? 1, 5, 6. Yeah, 6. Plus oxygen 16 times 3 plus 12.01, that's carbon times 6 plus 1 times 7. Remember, in paper 2 we are writing relative atomic masses to 2 decimal places, just like in the periodic table. Plus 12.01 times 7, which is 138. Okay, this one, don't quote me on that one, okay? You can double check if I messed it up, just you know how to find them all. Fine, next question. A student sets up a titration to determine the amount of iron 2 sulfate and in an iron tablet. They titrate the iron 2 sulfate solution with potassium manganate. Write the balanced ionic half equations to show the reduction of manganate, what is it, 7 ion, and the oxidation of iron 2 plus. Okay, there is not much space here. And we also need to write, use your answer to part 1 to write an overall redox equation for the titration of iron sulfate with potassium manganate. Yeah, I'll just write everything here. So we need, okay, so what do they ask? They want a reaction for oxidation, yeah, of iron 2 plus, where did it say it? Yeah, so we want oxidation of iron 2 plus by manganate ions. Manganate 7 ion, you need to know what it is. Yeah, so it's MnO4 minus. For IB, okay, for IB chemistry, this reaction is in the data booklet. That's a trick. If you know it, you can save like 2 minutes of your exam. So it is in table, I don't remember the table, 19. Yeah, so you see this reaction is the one that they ask about. This one. I will balance it from scratch just to show, but remember that chances are if they ask you to oxidize some weird inorganic stuff, it is probably in this table, in table 19. All right, so just try save your time, because also dichromate is there, also balanced already. Yeah, but we'll balance it from scratch. So all right, so first I would write 2 half equations. So what is happening? What is happening is that we're using MnO4 minus in acidic conditions, and we need to know that in acidic conditions MnO4 minus goes into Mn2 plus. That's the knowledge from, well, we do it in when we do transition metals in IB chemistry. We also know this reaction from organic chemistry when we do oxidation of alcohols. The dichromate is there as well. So this is factual knowledge that you hopefully that you know how it's happening. And then the other half equation would be iron 2 plus being oxidized. Iron 2 plus can be only oxidized to iron 3 plus. And then I will balance them one at a time. Okay, let's balance the first one. How do we balance half equations? First step would be to balance everything except for H and O. So I balance manganese. One on the left, one on the right, balanced. The second step is to balance oxygens by adding water. Balance oxygens by adding water. So I have 4 oxygens on the left, which means that I have to add 4 waters on the right. Then I balance hydrogen by adding H plus. Balance hydrogens by adding H plus. So I have 4 times 2, 8 hydrogens on the right, which means that I need to add 8 H pluses on the left. Fine? Fine. And the last step would be to balance the charge with electrons. So on the left, what is the charge on the left? It's -1 from here and 8 plus 8 from there. You know what's the number one mistake in all the exams I'm marking? Forgetting this 8. Yeah, so everyone says that, okay, it's -1 plus 1, 0. No, it's -1 plus 8. And that is plus 7. So the total charge on the left is +7. Now the total charge on the right. Manganese is +2, water is 0, so just +2. And now you have to balance the charge. So you have to make the charge balance. It doesn't have to be 0 on both sides. The charges just have to be equal. And you're only allowed to add electrons, not subtract. I mean, sometimes you can get away with subtracting, but don't do that, okay? So you just add electrons. Each electron adds 1 minus charge. So if I add 5 electrons on this side, on the left side, then it's as if I'm subtracting 5. You see, I'm subtracting 5, and the charge becomes +2. So now it's balanced. Yeah, good. If you just tell me if it's clear or not, you can just send me some message in the chat so that I understand that you're following. I can slow down or speed up depending on how you're digesting this information. Okay, yeah, and of course we could also check with the data booklet just in case, because this reaction is there, right? So you could have just copied it from there. 5 electrons, 8H plus 4H2O, so all good. Well, in the second equation, we just have iron is balanced, no hydrogens, no oxygens, we don't have to do anything. And then I just add an electron here to balance the charge, so it is +2 on both sides. Fine. And then to write the overall equation, this was part 1. Yeah, now part 2. So to write the overall equation, I have to add both half equations, and I have to make sure that the charges are, like the electrons are cancelled out. So I have 5 electrons here, 1 here, which means that I have to multiply this one by 5 to make electrons equal. So this becomes 5, 5, 5. And then I'm adding left parts separately, and that would equal to the sum of the right parts. So I would add this plus this. Let's do that. So I'm adding left parts. MnO4 minus 8H plus. I will write electrons for now. 5Fe2 plus. So I just added left parts of both equations, half equations, and that equals to the sum of the right part. So equal to, yeah, goes to this part plus this part. 5Fe3 plus and 5 electrons. Yes, 5 electrons cancel out. Obviously, if they don't cancel, it means that you did something wrong. We had to multiply to cancel electrons out. Well, that's it. That's our balanced equation. Next part. The iron sulfate solution is acidified before titration to stop the manganate ion forming unwanted manganese dioxide. What is manganese dioxide? MnO2. Explain the effect that not acidifying the iron sulfate would have on the final calculation of the estimated mass of iron. Okay, you can read it again. Yeah, so basically they say if we don't acidify it enough, the solution enough, then instead of forming Mn2 plus, we would form MnO2 with oxidation state of manganese being +4. Fine, yeah. And they say how would that affect the calculation of the final mass of iron. Right, so to approach these questions, what do we need to do? We need to think whether our titer would be larger or smaller, because how would we find out the concentration of iron? We would apply the ratio to MnO4 minus, right? So now it's in 1:5 ratio, which is the correct ratio. So we would have some titer of MnO4 minus. But now think about it. What if instead of Mn2 plus we formed MnO2? Would the ratio be higher or lower? Well, if it went to manganese 4 plus, or like +4, and then there would be 2 oxygens, so we would have manganese would have to gain less electrons, right? Because here manganese is +7, so it needs 5 electrons to go into 2 plus. If it was +4, it would have needed, like, 3 electrons instead of 5, okay? So the ratio would have been 1:3. Yeah, so it means that we would need a larger titer. So if we were to need a larger titer, yeah, because instead of like accepting 5 electrons, it would be only able to accept 3, so we would need a larger titer, which means that we would calculate larger moles of iron and we would estimate a larger mass of iron. Yes, so always always think about whether the titer would become larger or smaller. So in that case, it would become larger because manganese would only be able to accept 3 electrons or whatever, like less electrons than 5. Yeah, less than 5. So you would need a larger amount of manganese, of potassium manganate. And that's your 2 marks. Yeah, so you say what happens to the titer, and then you say that it would mean that you would have larger moles. Well, the calculated moles of iron would be larger because you would still calculate it as 1 to 5 ratio. Yeah, so you just increase your titer, but the ratio that you would apply would still be 1 to 5. So larger titer potassium manganate would result in the larger estimated moles or calculated moles of iron. And it means that larger estimated mass. Larger estimated mass. Next one. The student dissolves the iron tablet in excess sulfuric acid and made the solution up to 250 cubic centimeters in a volumetric flask. 25 cubic centimeters of the solution was titrated with 0.01 molar potassium manganate. The average titer was found to be 26.65 of potassium manganate. Calculate the amount of in moles of iron to ions in the solution and calculate the mass of iron in milligrams in the tablet. All right, let's do it this way. I will just answer this last question. Calculate the mass of iron in milligrams in this tablet. Let me copy this. And we'll just solve it as if it was one step. Okay, let's see. Can I do that? Yes, and the question is, and I'll also copy the question, calculate the mass of iron in milligrams. But of course, the first question we would solve as we are trying to find the answer. Yes, okay, that's the question. Right, well, let's see. So the student has a tablet. Yeah, let's let's draw it out. So there is a tablet of iron that contains iron 2 plus and something else. Yeah. And then we dissolve it in sulfuric acid. And the solution is made up to 250 cubic centimeters. So that's 250 cubic centimeters. Iron 2 plus dissolved in sulfuric acid. Yeah, that's that. And then we take 25 cubic centimeters of this solution was titrated. So now you take a tiny volume of that 25 cubic centimeters of iron 2 plus and titrated with MnO4 minus, and we know everything about MnO4 minus. Yeah, so we know that the concentration is 0.01. We know the titer is average titer 26.65 cubic centimeters, and our goal is to find the moles of iron 2 plus and then the mass of iron 2 plus. Well, let's see. So we always start from the end, the titration questions, right? So you always spot the value of concentration and the volume that is related to that concentration and find the moles. So the first thing that I would do is I would find the moles of MnO4 minus that was needed to react with that tiny volume of iron 2 plus. Yeah, that's the first thing that I would do. Then I would apply the molar ratio, because remember, we know the molar ratio, so that was the reason why they asked us to write down this equation. So the ratio of MnO4 to iron 2 plus is 1 to 5. So then from the ratio I will be able to find the moles of iron 2 plus, and that's it. And then from there we'll see what we do next. So let's start. So first I find moles of MnO4. I'll try to keep the question also there on the screen. That's a concentration times volume. Times volume, remember cubic centimeters must be converted to cubic decimeters, so 26.65 I divided by 1000 to convert to dm cubed. I don't trust my mental math, so I'll just do it on the calculator, to be on the safe side. So that's 2.67 to 3 significant, right? I put it to 3 significant because this is 3 significant, this is 4, so my answer is to the lower number of significant figures, times 10 to the negative 4 moles. That's moles of manganate, potassium manganate. So that's the moles that were needed to titrate that small volume. Okay, so now when I apply the ratio, I would find the moles of iron in 25 cubic centimeters. So now I find moles of iron 2 plus in 25 cubic centimeter sample. So it's 1 to 5 ratio as I showed in the balanced equation. Yeah, from there. You're following, right? So 1 to 5. Yes, so I'm applying that ratio. I found the moles of this. Now I'm finding the moles of iron 2 plus. So 1 to 5 times 5 times 5. To the calculator I will plug in the non-rounded value, so it's 1.33 times 10 to the negative 3. That's the moles of iron in 25 cubic centimeters, but the entire tablet, it was dissolved in 250. What does it mean? It means that to find the moles of iron in the tablet, I have to find the moles of iron in that beaker, right? So since I only titrated 1/10, yes, so I had 250 cubic centimeter of the solution, and I only titrated 25. So essentially, what did I find? I found 1/10 of the moles of iron 2 plus in the initial tablet. So then to find the moles of iron 2 plus in 250 cubic centimeters, here I would have 10 times more iron 2 plus ions, right? Because the volume is 10 times larger. So I would do 1.33 times 10 to the negative 3 times 10. The concentration, by the way, is the same, right? Because I didn't add water, I didn't change the solution. But the moles here are 10 times larger, well, just because the volume is holds. Yet the volume is 10 times larger, so it would have 10 times more moles. Well, yes, and that's it. So I found the moles of iron here, and then I can find the mass. Just moles times MR. Well, and obviously we assume that MR of iron 2 plus is the same as MR of iron atoms. Times what? Times iron is 55.85. Okay, 133 times 10 to the negative 2 times 55.85, which is 0.743. 43 grams. Yeah, okay, that's it. So all my iron that was in the tablet was dissolved into this acid, so I found the moles of iron 2 plus in that beaker, which means that I found how much iron I had in the tablet. Right, well guys, we're powering through, almost there. Last question. A reaction scheme for propene is shown below. Propene compound A, compound B, compound C. Okay, what is propene? Well, yes, that's the first question. State the condensed structural formula for propene. Condensed structural, it's when you don't show all the bonds. Yes, it's just essentially just condensed formula, not displayed. So propene, prop is 3, ene is double bond. Yep, that's the condensed formula. Then state the EUPAC names for compounds A, B, and C shown in the reaction scheme in part A. Well, okay, let's see. So this is my propene, yeah, CH2CH3. What happens if I add, how do I do it? Let me put it here. So that's an alkene, right? What happens if I add hydrogen over nickel catalyst? Well, alkenes undergo electrophilic addition, so hydrogen would just go into the molecule, so I would form an alkane. What happens when I add bromine? Also electrophilic addition, so, well, here actually it's like reduction, yes. This is definitely electrophilic addition, so I would include, like, add bromine at the double bond. So double bond breaks, I put a single bond instead of double, and attach Br and Br. That is compound B. And compound C, I do the same, but I attach HBr where the double bond was. And here two products are possible. Yeah, so I can attach H to the first one and Br to the second carbon, or the other way around. I know that my major product would be when hydrogen goes to carbon that already has the most H's. So here I will write the major product, but we'll see if they ask about it or not. So instead of CH2 it becomes CH3. Br goes there, CH3. So that's my compound C, but again, remember the 1-bromopropane is also possible there. State EUPAC names for compounds A, B, and C. Okay, so for A, where is A? A is just propane. B, what is B? B is 1,2-dibromopropane. Yeah, because you number from the side closest to the substituent. So 1, 2, 3. So 1, 2 dibromo, because there are two bromines. 1, 2. Dibromopropane. And C would be 2-bromopropane. Yep, that's for C2. Can you see? Yeah. So 1, 2, 3, 2. And bromopropane. And the last question, propene will also react to form an alcohol. State the reagents and conditions required for the formation of alcohol from propene. That's acid catalyzed addition. So we are just writing we don't even need the reaction. So we know the conditions of the reactions. It's a water vapor, and the catalyst would be concentrated sulfuric or phosphoric acid. And the conditions you just need to know. If you did GCSE, you know the conditions. If you did MYP, you have to memorize them now. So 300 Celsius temperature and approximately 60 atmosphere pressure. You can just say high temperature, high pressure. You would form an alcohol in these conditions. Okay, that was it. Still 38 minutes, not the fastest stream, but like shorter than the previous one at least. All right, so I let you go. Keep an eye on my live stream schedule. I haven't planned anything yet, but I think for next week I will plan the entire structure too for IB chemistry. I hope I can do it, and some practice questions for A level and IB as well. Yeah, so if you subscribe, you will be notified about new streams, and please react, yes, somehow. So if this content is useful, if you find that it helps you study, then I would appreciate if you can tell friends, subscribe, hit likes button so that I see some feedback. Right. Thank you for joining. See you next time.